dv by dv is 1. All right, so our family of normal vectors we can get from RU cross RV. So let's work that out. Okay, so I hat is going to have a sine V. J hat comes in with a negative sign, and that's going to be cosine V minus 0, so minus cosine V. And K hat is going to come in as U times cosine squared V minus a negative U times sine squared V. So I wind up with a plus sine squared V. And notice cosine squared plus sine squared is 1, so I've got a U there. All right, so that's RU cross RV. If we think back to our region, U is going to be between 0 and 1. Well, if U is between 0 and 1, the vector we're getting out here has a positive Z component. So this is the correct family of normal vectors. This itself is not a normal vector, but this is going to give us our correct family of normal vectors. Okay, the Z component is positive, and that's what we were looking for because we said we wanted to use the upward orientation. Okay. So is everyone clear on what we did on this page? Everybody good? Okay, so let's think back now. We're trying to do f dot ds. All right, so that would be integral over s of f dot n ds, and that should correspond to double integral over d of f dot, and because RU cross RV gives us the correct family of normal vectors, we can use that formula we saw before here directly. We don't introduce a minus sign here. All right, so you want to remember what was our F? F had component CYX. Our equation that gives the surface was this. And then there was a V at the end. So this is our X, this is our Y, this is our Z. And if we actually build the normal vector, right, it would be RU cross RV divided by the length of that. So we would get sine minus cosine. Whoops, wrong way. And then last component was u. All right, so this was RU cross RV. I can divide by the length of this guy. What would that be? So it would be the square root of sine squared plus cosine squared, which is 1, plus u squared. Come on. All right, so is everyone following along okay here? So if we plug into that f dot n to get the integrand in the surface integral, we're going to have to dot the family of normal vectors with our vector field. And remember that z is given by v, y is given by u sine v, x is given by u cosine v. Right, so we're going to have 1 over the square root of 1 plus u squared. First component is going to be z times sine u. So that would be v times sine of u. Okay. And then the second component, we're going to have y times minus cosine v. Oh, sorry, this was a v, not a u. Let's see, what was I doing here? I want second component. So y was u sine v. Oh, what did I do here? I'm sorry. Let me write this out so I don't confuse myself. Sorry. All right, so there's my vector field dotted with n. All right, so all of these things are going to be over that square root of 1 plus u squared. Z is going to be given by u cosine v. So u cosine v times sine v. And then we have y times the negative cosine. So y is u sine v times negative cosine. So I'm going to have a negative u cosine v sine v. And finally, we'll have x dotted with u, or x times u. So x is u cosine v. Damn it, what am I doing? Ah! All right. Let me just, sorry, too many vectors on the page here. All right, so, sorry. I apologize for getting balled up here. So I need the z. Z is v. I need the y. Y is u sine v times cosine v. I need more space. All right, so that is z times sine v. Z is v. Y times cosine v. So we have a u sine v. Right, that's my y. And that's times cosine of v. Then I need u times x. So here is x. U cosine v. All right, so the point here is that right, everything needs to be written in terms of u and v. And once you do that, you've got your integral expressed in a form that's going to let you actually integrate when you go to the UV plane. Right, and doing that, getting the integral to this form is going to be really the new wrinkle for this group of problems, right? Once you get it over here, you just have a double integral in terms of u and v that you have to deal with. So once you know exactly what our expression is in terms of u and v, well, we worked out f dot n. If we multiply through by the length of the vectors, that's going to get rid of this division by 1 plus u squared. And this is going to wind up as the integrand in this integral. Right, so I could have skipped to this directly, but I, for some reason, insisted on confusing myself. So f dot n has this division by the square root terms in with u and v in the integrand here, right? This thing is what we need over here, and we've got that result over here. This is not so easy to integrate, or not so easy to deal with directly because division by the square root 1 plus u squared, but we don't have to deal with it directly. We want to convert it to the double integral over d. Remember, ds is this area distortion factor times dA. So we're going to have to multiply through by this guy. And this circled quantity is going to be our integrand for the double integral over d. Okay, and v sine v, that's something we can integrate by parts. U squared cosine v, well, I can integrate u squared with respect to u. I can integrate cosine v with respect to v. That's not a problem. I can integrate u for this middle term. Sine v cosine v, I can integrate by substitution, or I can use the trig identity that sine of 2v is 2 sine v cosine v. It's not hard to integrate. And because, where was it here? Our region is a rectangle, right? There's no problems with these integrals that come up because of the region, right? We have to integrate powers of u from u for u going from 0 to 1. That's not a hard problem. We have to integrate sine or cosine with respect to v from 0 to pi. That's not a hard problem. So the hard work, right, for these surface integrals is getting them to the double integral in parameter space. Okay, once you get there, if you're expected to actually do the integral, typically it's not going to be so bad, right? It could in general involve any integration strategy, but the problems that are given in the book, typically, they're not so bad once you get them set up. Okay, so I'm sorry if I made a dog's breakfast of that, but how are you guys doing? Following along, okay. So I apologize for the noise. There's some construction work going on in the apartment next to me, which is distracting me. I don't know if you can hear it or not, but I apologize for the background noise. All right, so let's try another one of these. Actually, let's try 29. So we have a vector field. The components are x, 2y, 3z. And our surface S is the cube with vertices either plus or minus 1, plus or minus 1, plus or minus 1. Okay, so so the cube is centered at the origin, and it goes out to plus or minus 1 in the y direction, plus or minus 1 in the x direction, plus or minus 1 in the z direction. If we project onto the xy plane, sort of the equator of the sphere is going to look like this. Okay, so think of this square in the xy plane, and then we're going to go up or down by 1 unit in the z direction to build the cube. Okay, so that's our surface. We know our surface integral. Now notice when you have a cube, right, you've got corners and edges, right? It's going to be very difficult to try to come up with a parameterization that gives you the whole cube, but you don't have to. You can divide this up into the faces of the cube, and on each face, you've got a normal direction, right? So the front face of the cube where x is equal to 1, y and z go between -1 and 1, the normal vector is going to be a unit vector in the plus x direction. I forgot to say on x equals 1. Okay, and the back face is going to be when x is -1, y and z both go between -1 and 1. What's the normal going to be on the back face? Well, it's just going to point in the negative x direction, right? So what's it going to be?
Would it just be -1, 0, 0?
Yeah, that's it. And for the side faces, the way we've drawn the cube, the face on the right is going to be y equals 1, x between -1 and 1, z between -1 and 1, and the normal vector would be 0, 1, 0, right? Unit vector in the plus y direction. The left face of the cube would be y equals -1, x and z both go between -1 and 1, the normal vector would be 0, -1, 0, and so forth, right? And then we have the top and the bottom faces. So here's an example where we don't want to skip directly to this version, because we actually have an easy way to get our hands on the normal vector directly, and we're going to have to use different normal vectors on different faces. So the standard assumption, which I passed over here without highlighting it before, when you have a closed surface that you want to do a surface integral over, unless you're told otherwise, you always want to use the outward family of normals, which is what we did here. Okay. You could obviously use the inward normals, so that would just be -1 times all the normals we mentioned. But here there's no nothing contradicting the standard assumption, so we're going to think about using the outward normals. All right, so we want to break our surface into the 6 faces. So let's think about x equals 1, y between -1 and 1, z between -1 and 1. Right, so that is what we call the front face of the cube here. Right, so for that surface, we can use y and z as our parameters. Okay, and we said that the normal is just going to be a unit vector in the x direction. So what is f dot n going to be there? So we had x, 2y, 3z. We're going to dot with 1, 0, 0. That's just going to be x. And on this face, x is equal to 1. So the integrand f dot n is equal to 1. Okay, so was everyone able to follow along that development? Any questions there? All right, so given that that's a flat surface, right, we're integrating 1 ds over a square, right? That's just the area of the surface. And what's the area of the front face of our cube here? Well, the side of the cube is 2. So that area is just going to be 4. And that's exactly what you would get by converting your surface integral to a double integral over your parameter region, right? So over D, you would have n, which we know is 1. So we would need Ry cross Rz, absolute value dA. But look at our parameterization. X is 1, Y is Y, Z is Z. So RY would just be 0, 1, 0. RZ would just be 0, 0, 1. So this is the unit vector J cross with the unit vector K. Oops, RY cross RZ. Those are perpendicular and each are unit vectors. So I know when I take the cross product and take the length, I'm going to get 1 here. Right. In fact, J cross K gives you I, right? So, and that's going to have length 1. So your integral becomes minus 1 to 1 in both Y and Z of 1. Integral of 1 dy for minus 1 to 1 is going to be Y, for minus 1 to 1 is 2. So you're going to integrate 2 again. It'll produce a factor of 2. So you know you're going to get 4 out for that. All right, so you didn't really need to go here because the surface integral actually was of a particularly simple type. And what you'll find for the other faces in this problem is that you're going to be integrating a constant on each of the faces. So you don't actually really need to go to the integrals over the parameter spaces. You just have to remember that if you have surface integral of a constant, right? As long as you're integrating a constant, just like for any other type of integral, you can pull that out in front, and integral of 1 ds over the surface gives you the area of the surface. So if you have a way of getting the surface area easily, then you can use that. You don't have to directly, you don't have to convert this to a double integral. Right, so if you were dealing with something like integrating over a square or a rectangle or a circular disc or a sphere, right, there's formulas from geometry that will give you the surface area in many cases. All right, so that's where we have to stop for today. Let me stop sharing here.